Hello everyone, and welcome back to our video review series here. Today, this is the very first video for Unit 8, which is on chi-square testing, or more generically, hypothesis testing or inference for categorical data. And so this first video here is going to cover the chi-squared goodness of fit test. And then the next two videos are going to cover essentially what is the same test mechanically. It's just a matter of like what question are you being asked, which is the chi-square independence and then the chi-square test for homogeneity. So let's jump right into it, take a look at what chi-square is, and then take a look at an example or two. So a chi-square goodness of fit testing, what it's asking you is essentially, does my sample match my expectation? So the idea is that we have an expected distribution of a population, and we're going to take one representative sample to determine whether or not we have evidence that it does not match the expected distribution. So that's going to be one thing that's very important. Your null hypothesis here is always that it does match, and your alternative is always that it does not match. We just have to put that in context of the actual problem. So it's different in two ways. One is that this is all for categorical data, right? And the other way is that my hypotheses are now in words, as opposed to saying something like mu equals 5, or mu1 equals mu2, or p equals 0.7. It's now sentences as opposed to numbers. And so when we take a look at our hat North Carolina, right, for my hypotheses, the null is going to be that we do match the expectation. The alternative here, which I think is very important to note, is that at least one category doesn't match. This part right here is probably the most important thing here. We're not saying every category is different, but if one category is different, then your sample does not match the expectation. So you may have one or two that don't match and two other categories that do, right? But our alternative is that at least one is different. Because if the null is that everything matches, the complement of that, if you think probability-wise, is that at least one is going to be different from the expectation. For our assumptions, we still need a random sample. For your sample size now, this is very important. It's that all of the expected numbers are greater than or equal to 5. I cannot stress this enough, that it is the expected number. They will try to trick you on the multiple choice questions and give you a table where one of the observed values is less than 5. But that does not matter. What matters is that the expectation, or the expected number in that particular cell in your table, is 5 or more. I've seen it a million times for a chi-square multiple choice that they have an observed of 2, but the expected in that cell is actually like 7 or 8, so the test is perfectly fine. So don't be fooled. The test is a chi-square test, and it's specifically a chi-square goodness of fit test. The formula for all chi-squared tests looks like this. The sum of all observed, the observed minus the expected squared over the expected. And so a lot of people liken this to like summing up a bunch of like percent errors, even though it's not percent error because that would be the absolute value in the numerator. But that is essentially the idea of we're looking at how far away percentage-wise-ish we are from the expectation. And then for my numbers, I'm going to list the chi-square value, the p-value, the significance level, and your degrees of freedom here is still n minus 1. But importantly, n is the number of categories. It is not your sample size. It is the number of categories in your sample. And it's the same idea where if you know the total sample size, and let's say I have 4 categories, if I know how many are in 3 of those categories, I know how many have to be in the 4th one. And then my conclusion is the same as every other hypothesis test. We either reject or we do not reject. And then based on that, we either have evidence or we don't have evidence. So, how do I actually calculate my expected? Well, here's the deal. We have 2 different scenarios for that. The first scenario is that you have some sort of uniform expectation. This formula is now incredibly simple. Your expected just equals n. Maybe I shouldn't say n because we just talked about n being the number of categories. It's going to be your sample size over the number of categories. The other way you have it is some sort of percentage basis. Let me underline these here. And if that's the case, the expected equals the sample size times the percent in that category. All right, so I'll take the percentage and multiply it. What's very important, again, common mistake, what's very important here is that it is the total sample size. It is not the observed number in that category times the percentage. It's the total sample size times the percentage. And so let's take a look at a question here. And now if you're one of my students, we've done this question before, right? It's the moose habitat acreage deal. And we're looking at, do moose have a preference? And I very purposefully picked one of the percentage basis ones. So that way I could show you what I mean by this. So if we roll through this here, my null hypothesis is that moose have no preference. My alternative is that moose do have a preference. And this is the same way or the same thing as saying at least one category is different. I forgot to add the E to preference there. And so there's my hypotheses. If you noticed here very quickly, assume all conditions for inference are met. My favorite sentence ever, right? So for my assumptions, we have assume all conditions met. But at least to show you how I would get the expecteds here. For habitat type 1, I would take 117, which is my sample size, times 0.34, and that gives me an expected number of 39.78. For habitat type 2, I would take 117 and multiply that by 0.101, which gives me an expected number of 11.817. And so this is how you would actually compute the expecteds here. Right? So my test now is a chi-square goodness of fit test. And from our calculator, you get a chi-square value of about 43.7, a p-value of about 0, and my degrees of freedom here are 3 because I have 4 habitats. I have 3 degrees of freedom. And so, for my conclusion here, we reject our null hypothesis. It does seem, based on this question, that moose do have a habitat preference. So, I hope that was helpful, and I'll see you guys in the next video. Bye.